Okay, we will talk about uh, engineering stress strain curve. Stress strain curve. We know that there is a stress value of stress, which is force per unit area, and value of strain, which is a change in length by original length. Here, some considerations are some assumptions are taken that the cross section area will remain same for all the deformation cross section area, and this is not true because it deforms. The cross section area will change. Hence, these are the terms of engineering strain. We use these are for engineering terms. This is engineering stress, and this is engineering strain. What if the instant area is used? Instant area, that is sigma upon force upon area of instant. This will be true true stress and true strain. True strain is defined as final length upon initial length. Ln of final length is initial length upon change in length by initial length. This is ln of 1 plus, and del L by L is E, which is engineering strain. And similarly, true strain can be derived as engineering stress. A true stress is engineering stress 1 plus. So this is how engineering strain true strains are. Let us talk about stress strain curve. Uh, what if there is a this is a graph. There stress is plotted against a strain. Firstly, as we uh, pull the bar apart, let us talk about the very tensile stress test. As we apply the stress, the strain will change linearly up to some point. Very linear. Okay. Okay. So this is known as proportional limit. A is known as, I will not write here, but it is proportional limit. And just above the proportional limit, there is elastic limit. There is elastic limit B. Now, after elastic limit, this bar starts to yield, starts to deform like a very plastic material. It is a very slight impact. So this is C. This is upper yield point. Yield point. Okay. So uh, after the, if we continue to if we lower the stress slight little bit, uh, the strain also increases. If we lower the stress from upper yield point, the strain also increases, and it will known as lower yield point. Yield point. From lower yield point up to linear change in stress, there is a ultimate stress UT. Beyond ultimate stress, the necking starts. Necking is the process of like this. If this is a cross section, a small neck tries to form at the cross section, and it starts, and it occurs with fracture. Okay, fracture occurs after the necking, and this is ultimate tensile stress. If you further change the stress, value of stress, it will create a point C, D, E, F at which necking occurs. If it is, if you consider the account of engineering stress, but what if true stress? True stress occur in case of true stress or true strain. The curve looks like this because in true stress the area after making will decrease, and this will increase the stress, yeah, stress value. So it will propagate like this. This is true, and this is engineering. This is true, this is engineering. Now in stress curve there is there are different points like up to the elastic limit. There is the absorption of elastic energy, yeah, absorption of energy. This is known as resilience. Resilience. Toughness is there, which is energy absorbed up to fracture. Toughness. And modulus of resilience is mode of resilience is proof resilience by volume. What is proof resilience? Proof resilience by this volume, up to where volume of energy consumption. Proof resilience is the maximum energy that can be absorbed during this elastic limit. Okay, and this is softness. Now we will talk about Hooke's law. What is Hooke's law? Hooke's law is nothing but we know that the behavior of stress and strain is proportional up to some limit known as proportional limit or elastic limit, if we consider elasticity. This is normal stress. Normal stress, I've talked about normal and shear stress and normal and shear strain. So sorry, normal stress will be proportional to normal strain up to the proportional limit. So using this relation, we can derive stress if there is strain given and stress if there is strain given, and also we can derive the behavior of the, if you know up to this point, data up to this point, and we know the proportional limit, we get all the values of here. Okay. Now there is proportional limit is uh, we put the constant e here. This e is known as Young's modulus. Young's modulus of elasticity. Okay, so if there is a shear modulus, is this shear stress? Okay, okay, sorry. Shear stress is shear strain. So tau equals to z. This is shear, right? Shearing has also a proportional limit. Uh, this is generally tensile compressive shear stress strain curve. Tensile compressive stress strain curve. Now, uh, this g is known as modulus of rigidity. What? Young's modulus? This is modulus of rigidity. Rigidity. Okay, sorry. Rigidity. And we know that bulk modulus is in a 3D. There will be in the 3D compression or tensile or any kind of loading, there will be volumetric strain, and bulk modulus is, we know Young's modulus, we know modulus of rigidity. Now there is a concept of bulk modulus K. It is nothing but normal stress, normal stress upon volumetric strain. Volumetric strain. This is the normal stress. Okay, these are Young's modulus, modulus of rigidity, and this is bulk modulus. Bulk modulus. So we have talked. We have known about Hooke's law. We have known about the modulus of rigidity. Okay, modulus of elasticities. This is Young's modulus. This is modulus of rigidity, and this is bulk modulus. Let us talk about the relation between them. Okay, we know that E. What is E? E is Young's modulus equals to 2 times modulus of rigidity 1 plus mu. This is the Poisson's ratio that I've talked in strain, the video of strain. E is also equals to 3k 1 minus 2 mu, and E equals to 9 kg upon 3k plus C. These all are true for isotropic material. What is isotropic material? Isotropic material is uh, thus that kind of material where E is constant. E is constant for all direction. Okay, or same in all direction. Anisotropic means E can be different from one direction to another direction. Anisotropic. Anisotropic is E is not constant. E is not constant material. Okay, isotropic and anisotropic material. What is a homogeneous material? There is a concept of homogeneous material also. Homogeneous is we know that equally distributed. It is E is same in all point in all direction. Okay, in all direction. This is homogeneous. It is equally distributed material properties. So we've known about isotropic and homogeneous material, uh, volumetric strain, bulk modulus. Okay, I think this is it. Thank you.